All right, so I got arm twisted into amplitude amplification. It can be referred to as magnitude amplification, but he gave a couple reasons why he went with this, but also said that the academic literature doesn't use this term. So that's just some interest, some things to know up front. In all honesty, this chapter is pretty easy, except it's also like, why am I doing any of this? So like, I think the concepts are easy enough to grasp, but we really have no idea why we're doing anything. So, well, I guess we are trying to switch the phase with the magnitude, but there's certain things in here that is like, so I might as well just talk. So we got this flip and mirror thing going on, right? And in order to flip, you have to already know what you want to flip. So this whole equation formula relies on the fact that you already know what you want to flip, which you won't always know, right? We're like hard coding it. So it'll be interesting to see where this actually ends up. So I threw together, so I altered one of his to better represent what the book was. So if we just step through this.
I'm sorry, I'm just going to interrupt you. Can you share your screen so we can see?
Oh, I am not sharing my screen.
Yeah.
That's all right. I wasn't showing that much until just then. So
thank you. Okay, all right. Great. We can see it now.
Excellent. So like most things, we do a Hadamard, and then let's change the colors here. So this flip, essentially, we got number 3 highlighted, and the phase is 180 degrees. Now if we do a mirror, we see that the magnitude of this has increased. And if we were to try and read and wanting to get the value 3, we would have a high percentage chance of getting 3, but not as high of a percent as we would like. So then that leads to iterating. So doing the same thing here, we've highlighted 3, but it turns out that if you go through, go twice, it gets bigger, and if you do it 3 times, it's even bigger. But after the 4th time, it starts going in the opposite direction. And the reason it starts going in the opposite direction is because the phase only has 360 degrees. So at some point it starts repeating itself. Let's see. So now I have, this one is pretty much the same thing, except now it gives us the probabilities down here. So we can see that the 3rd one gives us 96% chance. And with this, you can start doing marking multiple items. So let's say you wanted 0 and 1, or 0 and 15. I like keeping them separate. So we do that. Let's change the colors. So see, that already got worse. So this one's actually better. So how do you know how many iterations that you should use to get the best result? And that is given to us. Where's the formula? There we go. Here's our formula. So pi times the square root of 2 raised to the n divided by 4. So let's walk through that. So if we have 4 qubits, so n is the number of qubits. So 2 to the n is 16. Square root of 16 is 4. 4 divided by 4 is 1. So we're actually left with pi. So the optimal number of iterations is 3, since we can't do a 0.14 iteration. So as you go, so where's my, no, have an Excel here. So if you get, when you get to multiple bits, the equation changes. Well, in actuality, it's the same equation. It just, we weren't showing this m before. So the m is the number of marked items. So in this case, we have 2 to the 4, which is 16. And m could be anywhere from, well, 1 to 15. I guess you could put a 1 to 16, I guess. You can't do it with 0, because that will blow up. But if we look at this, if we look at the Excel, just really quick, and let me switch this. Not that one, this one. So here's the optimal number of iterations. So the more items you mark, the fewer iterations you need. However, it turns out that these won't give you as good of results, I guess, as just doing this again, but backwards. So instead of saying I've selected 9, you would say I selected 7, and negate what is the success. So 1 through 8, your friend. 9 through 16, not your friend, apparently. So let's see. Let's go back to this here with the multiple bit flipping. If we do, 4 numbers here. Let me go right here. Let me get to the first one here. We see that it only has the 4 ones that we actually wanted, right? So in previous cases, we were not so lucky, right? Everything still has a bit of magnitude, but once you get to 4, come on. Once you get to 4 marked items, then you have a 100% chance of hitting one of the 4 marked items. And it does get worse. Well, it repeats itself. So every 3rd time, it will have the correct results. So the 1st time, the 4th time, 7th time, etc. Another interesting one is if you try to mark 7. I don't know why 7's a magic number, maybe because it's 1 less than 8. I don't know. But if you mark 7 numbers, I think that's it. What do we get? I don't know what we get. What was I supposed to get?
Isn't it that if you mark more than half of the values that you should toss it away and throw it away? There's two variables, right? How many iterations you should run? Well, with 4 items marked, 1 is sufficient. And then there's a knob to turn of how many can you mark effectively.
Right, and that's where he talked about that you shouldn't go over 8. So we have 16 items. Once you get to 8, if you're going to go higher, you actually just inverse it. And instead of saying I mark 7, you say I mark 6. Or instead of I mark 9, I marked 6. No, I can't, what are the, I don't know what the, 7. So instead of 9, instead of saying you marked 9, you actually marked 7. Did I get that right that time?
Yeah, that sounds good. Can you scroll down on the right so we can see the percentages? I'm just curious about that.
What is it? Oh my goodness.
Does this one have the output?
Yeah. So it looks like here we have almost 0%. Practically 0. Practically 1. All right. So I'm trying to, does anyone remember? There was something special about 7 marked items, and I can't remember what it was. So here, we see every so often it gets a really high percent. But it says, so we have a really good chance of getting 1, but because there's 7, I guess maybe it's not as useful because there's so many, I guess, I don't know. But then the interesting thing happens, at least with 8. And with 8, it just all falls apart. So now we just end up with a 50% chance of anything of marked or unmarked getting hit. So what do these things represent? That is the probability does anyone know what this means?
Yeah, I think that's the probability that one of your marked values will come up. So the ones that say 99999, it's nearly 100% that the one that comes up will be one of the selected items.
Okay, so if we look at this chart, hold on. It's hanging off the screen over here. So here, 8 items marked, the chance of getting a marked value probability is 50% all the way across. And we can see that after each mirror, they all, you know, they have the same magnitude, and so that's where I'm confused on what this is.
The output's not clearing. So the one you just ran will be down at the very bottom of that output list.
Oh yeah.
So every time you hit run or step through, it's adding a number to that output.
Mm-hmm.
Oh.
This is where we need to run Mary's.
Yeah.
Yeah.
There we go.
There you
Oh
go.
man, I was so confused.
So can I jump in here with a little bit of context, because
Sure.
You know, I think that for people who have not done machine learning, this although the mechanics of the chapter are understandable, it's exactly what you said, Dan. It's like, okay, I get it, but I have like no idea why this has anything to do with programming. So just kind of have any of you done machine learning programming? I didn't think so. So let me just, first of all, it's going to come up in the book, like in chapter 13. So, but let me go back to what was presented in chapter 1 and just something I know about quantum computing. The applicability of it, as I mentioned, and I think is covered in the book, is in problem decomposition. And so you have a classical part and you have a quantum part. And basically you're going for a quantum speed up. And machine learning is not the only application of this type of computation, but it fits so nicely because machine learning is always probabilistic, always. So if you kind of go in with that frame and you think about, okay, I don't understand all these probabilities and like probabilities of this and that number, the sort of meta thing is if the problem is decomposed correctly, which is a difficult part, offloading some of the calculations onto the QPU registers has the possibility of the quantum speed up, which is one of the reasons why people are so interested in quantum computing. Because in the world of machine learning, you are doing, I mean, you guys have probably had stats. Has everybody here had stats? Or have somebody have stats, right? So you're looking for median mode, you know, the range basically of the values that are going to come back from a computation. And you're looking at the probabilities of a range. I mean, the simplest possible thing in machine learning is linear regression, which probably you guys can all remember y equals mx plus b, right? With the line, like you have the x and the y and you have the dots, right? And where does the line, does it go up? Does it go down? You know what I mean? Like where is the center, right? And then are the dots above it or below it? You know, what's for each dot, right? So that's the simplest possible machine learning. What is the probability of at a certain x? What will be the highest, the probabilities of the possible y's? And so we'll see this, and I'll just give you a preview of it, because to me at this point, it's really hard to keep going if you're just thinking about applying this to sort of non-probabilistic computing, because you'd be like, this is nonsense. Like you're saying, Dan, it's like, what would you do with this, right? So the thing they talk about in the book is looking at pixels in photographs. And we all know that internet scale applications of rendering photos will have different levels of depth depending on internet speed. It's very relevant to where I am because it's slightly slower here. And we've all seen the photo kind of come in granular and get sharper and sharper and sharper, right? That is a problem that you use this type of computation for, because you can calculate the probabilities of what would be the likely color of the pixel faster. Does that make sense? Because you offload to this type of computation. So one of the fun things about learning quantum programming is really once you go through it, if you want to go beyond what's in the book, the next step is to start to tie it to machine learning, because that's really where it's having most of the applicability in terms of some kind of practical application. Because the kind of programming that I think everybody on this call except me is doing, what this is doing, I don't think there is an application. So to go back, Dan, your instinct was right. It's like, what is this nonsense? I don't know what this is, right? So it makes it kind of doubly hard to learn if you haven't done machine learning. So I just thought I'd throw that in there because I could just see everybody's face kind of like, okay. The other kind of big thing that this chapter is addressing is how do you compute while entangled? And Nuri, you had the excellent question. I think Jeremy, you brought it up too. Like, okay, we shift the phase, but like, so what? Like, why do we care? Well, we're starting to learn why we care, because we can entangle and compute while things are entangled. Because as soon as you read, you're done, right? So that where kind of the heat happens is when you are doing this type of stuff. And we'll see in the next chapter that this is applied using transforms. It's called a Fourier transforms, yeah. So it takes it to the next level of sophistication. But I think the concept's really, really hard if you don't have machine learning. So I don't know, does that help at all, or did I just muddy the water?
It does. I think maybe I should learn machine learning.
Yeah.
Yeah, that was one of my questions. Where's a quick intro? Where's the Lynn Langet kindergarten version of machine?
Well, what they teach the kids in school is the Python library Scikitlearn. And the website for Scikitlearn is really pretty good. Like it has, like linear regression, it has the little thing, the line graphs, you can see it. Logistic regression is similar, but it's what classification, what category, rather than what data point. So that's a good starting point. Of course, I do have courses. Of course I do, but they're cloud-based. So I don't know if you care about that. They're GCP or AWS machine learning, because the cloud vendors are supporting kind of a 3 different levels of machine learning. They're supporting machine learning where you rate the model. So you'd make your linear regression model. The other thing that happens with machine learning that is another application of this kind of computation is something called hyperparameter tuning. Because in machine learning models, you're putting in the tolerances. If you think of the, line graph, the X and Y, and the line going here, and the dots are here, here, here. The tolerance is how far away can the dot be from the line before the line moves, right? And so, I'm oversimplifying, because when you get into some machine learning models, you're n-dimensional. So like 5-dimensional, 10-dimensional. And then you basically are creating what's called a hyperparameter grid to kind of, I always think of it in my mind as like spinning the cube and sizing the cube, right? To figure out like where is what's called the local minima. It's where is it closest to the curving line at that point. So that requires a lot of possibility. Try this possibility, try this possibility, try this possibility. And then again, you decompose the problem, you offload theoretically onto the QPU. Where it's being done now, and I mentioned this in the previous week, is you offload to a GPU or a TPU, which that's kind of how things happen today. In particular, the more complex machine learning, the neural networks, which is basically a n-dimensional curved grid. So it has, calculus, applied calculus. So there's a lot of different possibilities. That gets offloaded, the linear operations, onto GPUs for like 100 times speed up. But the potential for QPUs is 1,000,000 times speed up, right? Because all, or faster, all possible combinations at once. And that's kind of the road that, well, at least I've been going. I'm sure that there's somebody who's figured out some sort of application for QPUs for classical computing problems. I'm sure they have. But because the focus of my work often includes machine learning computations that are pretty gnarly because of the width of the genomic data. This is actually one of the reasons I'm here, because I want to start to learn the possibilities here for getting those quantum speed ups. So I don't know, that's kind of a long spiel, but you have to start. I don't know. Start with linear and logistic regression and random forests. Those are the basic ones.
I don't even, what did you just say? Which ones?
Linear regression, logistic regression, and random forests. So decision trees, groups of decision trees. Those are like the 1, 2, 3 of machine learning. I do think if you're inclined, number one, so much of programming work is going that way. So it sort of just keeps everybody more relevant. Plus it's fun and interesting, but it will make learning quantum programming more rewarding. Because I think otherwise you just want to like slam your head against the wall and say, why is this so non-deterministic? I just don't understand. Right?
Yeah.
I remember that I implemented in my early days, I was doing online dating for a large online dating website. And one of the things we had to do is text classification just to help customer service sift through and make sure, try to catch people who are just not appropriate. So anyway, so simple Bayesian algorithm. And very quickly you see that suddenly, first of all, bounce against the numerical, all of these overflows and underflows came into the math really quickly with not a lot of data points. And then, you know, even though it seems like the formula itself seems innocuously linear, it turns into a n times n or n times factorial because you have to do set operations, which, you know, try to classify, it's clustering essentially. You're trying to say, does this word belong in this bucket or in this bucket, or do this whole essay belong in this bucket or that bucket? And we wanted an answer, right? But all we wanted to know is whether it's higher probability that the answer is here or it's there. Really, we wanted to know, you know, should we accept this essay or not automatically, or should it undergo manual review by somebody? So I can totally see probability things translating really quickly and into very concrete, you know, deterministic things. You only look at it as deterministics because the answer fits in a Boolean. But you can flip the Boolean. What drives flipping that Boolean could be a multitude of statistical, you know, probabilities. So
Well,
I think that's another thing to get over, is this idea that, you know, because our end result is a number, that means it has to be deterministically so. It could be non-deterministically so.
Yeah, that's a really important point. But to even go beyond what your use case, which is kind of like a spam classifier. So it's a relatively basic use case. Just to give you guys kind of a look into, one of the projects I worked on, the human genome is 3 billion letters with a B. And I was working on optimization of a custom algorithm for what's called wide dimensional analysis. And it could consider up to 10,000 dimensions. So, you know, think about that, n by n by n with 10,000. When initially we were working with the problem on the shared cluster, it took 500 hours to run one test, and it would fail about half the time. And that's very common in genomics because of the amount of data and the complexity of computation. It's all probabilistic, all of it. I had another client doesn't really matter where, but their computation took 2 weeks, 2 weeks on a mainframe to run like the most basic thing they could do. So the volumes of data times the probabilistic compute is, you know, forcing different paradigms for computation. And that's where I'm hoping that application of QPUs and quantum comes in. But yeah, you have to start first. You have to start with, you know, like the spam classifier, like Noreen was talking about. But you know, it's not just genomics too. I mean, smart buildings. I had one client who had, 25% of the schools buildings in the United States. And, you know, they were just IoTing everything and building models against all the event data. So, you know, the datafication of our world is moving so much of our computation to this sort of probabilistic approach. Because the way we've been thinking before, throw it all in a database, do a SQL query, you can't. It's not possible. Even if you wanted to spend all your money, it won't even work. So I don't know. Again, I don't know if I'm just too pie in the sky there, but the book does, I think it's in chapter 13. They actually apply this and what's in the next chapter to that speeding up the pixel rendering problem. So does that make some sense? Does that kind of help give context to this?
Yeah, I think so.
One area that I was kind of looking at, and this is where I was a little confused too, is the first several chapters of the book, we've been playing with magnitude the whole time. And I thought, well, that's our, I've got 16 possible answers. I'm going to manipulate the magnitude so that the few that I think are the most correct would come to the fore. And it sounds like he's saying, well, we're still going to do that, but we're actually going to do our computation on the phases. And then we're going to mirror those so that those particular qubits are the ones that'll hopefully come up to the surface. And so it almost sounded like, well, are we changing what we did? Should we? I'm still, yeah, I kind of want the phase computation seems to be what he's concentrating on. And that's fascinating to me, but it's almost like, okay, I'm going to do all my calculations in my phases, and then I'm going to take those phases and somehow manipulate the qubits so that those are the ones I'm looking for. I'm still trying to put the two together versus what we did in the first 5 chapters of the book.
Well, the way I think about it is the computation occurs during the entangled portion. So the question that Nuri asked last week was just really on point. It was like, why do we care about basically where the line is pointing and how big the circle is on the inside? Because that is where the computing is happening. Once you read it out, you're done. So it's very different than, you know, set the value of a variable, do something to it, see the new value of the variable. It's you get everything entangled, and then you flip it and mirror it and get your information out, and then you set it back. But the compute, or I call it the heat, basically, is happening what I think of inside rather than outside. And I don't know if that metaphor is useful, but that's how I think of it. Like you have n number of qubits and they become sort of entangled, and then kind of the compute happens inside. And then when you're done, you just return them back to normal. Does that make any sense?
Yeah, it almost sounds like, okay, the phase is where you're computing a lot of your information. And the entanglement, yeah, you're somehow manipulating in such a way that, again, the calculations that you're really interested are the ones that are going to come out of it. I guess this entire time I've been thinking, oh, okay, the magnitude is where we're doing our calculations. That's almost, now it seems like that's almost relating all the different qubits you're interested in, but the phase is where the actual information is. I'm not sure if that's correct.
Well, I think that he covers it in the beginning of this chapter. Dan, can you go back to the beginning? I think like the first page of this chapter.
Yeah, and that's what I'm looking at.
Yeah, he explains how, you know, the relationship between the two things, if I remember correctly. There, okay. So very simply, amplitude amplification is a tool that converts inaccessible phase differences inside a QPU into readable magnitudes. So the phase information is not accessible as phase information, but when it's converted to magnitudes, those magnitudes are readable. Does that make sense?
That makes sense, but why are we concerned about phase difference?
So here's one. I'm having a thought here. I don't know how well vetted. So we went through some basics, and you know, we're trying to think forward. He's trying to give us some groundwork to get into places. And those phases, it turns out you don't like read them directly, but you can read the qubits as a quote unquote register, or treat them as a register, and get digital information in the end, right? Because once you do it, it is the end. Mm-hmm. So in order to make it readable as digital, as a number, as a result, you want to transform the things that you can't see, those phases, into some kind of number at the end that you could read out and symbolizes something for you. Furthermore, you want to keep it as your secret weapon until the end, because you could extract some maybe bits of information from the QPU into another sidebar, sacrificial qubit or something, while you're doing stuff to observe it, or internally when you have algorithms that need to get a result of a calculation and check against it. So it's common in, say, machine learning, like in I think it's in neural networks. You have a fitness function, and so it's kind of evolutionary. You have a survival of a certain probability or a certain function or a certain set of values that go into the next generation if they pass the bar. So in order to come up with these values and compare to repeatedly until you get bigger and bigger magnitudes or more significant tendencies, then you need to have that feedback within your program without performing a read.
Yes.
So by keeping all of this, what Lynn said in the beginning, by keeping all computation unread, by keeping it in that superposition and doing the math under superposition, you're making it very opaque. So you need a way to access this information for within the algorithm, and you might want to keep some information coming out while the algorithm is still remaining in its entangled state.
So speaking of state, for all of us who are coming out of OOP, it seems to me this is how you maintain state in quantum programming. It's not a one-for-one as OOP state, but it's like I was inelegantly saying, when it's all kind of jumbled up together, the state is in there. But when you do a formal read, then it's gone.
OLP is what?
OOP, like C#, object-oriented programming. So I don't know if that helps. That's the way I think about it. I don't know. Anybody have anything else to add here? Dan, I'm sorry I like kind of ran over your presentation, but I just felt like it's, I learned machine learning not that long ago. And so I know how I felt before machine learning and after. And it's kind of a different world of programming, probabilistic programming, that I'm glad I went into, and I would really advise everybody else does. Because it's, I mean, you know, you think of like OOP versus functional, and you go, okay, I'm like, you know, I've got a lot of tools in my tool belt. You do, but, you know, deterministic versus probabilistic, I think is a much wider chasm to cross, much wider. So.
All right. So, so phase cannot be read directly. Is that correct? We have to read magnitude. So we do this phase magnitude swap so that we can read the magnitude, which used to be the phase, right? Because we wanted to get that data instead. So we switch it. Now we can swap it back and continue doing other calculations, because a mirror is, what do we call that when you can undo it? It's undoable.
Reversible?
Reversible, that's a good one, yeah. Anything anyone wants to add until I move on?
I found it a little, in this chapter, in a previous chapter, I found it a little curious that the way things multiply or iterate, it produces a longer program in a sense. And the reason, like, if you look at microcomputer architecture, it's quite common to have, you know, something read from memory, and then you have an addition. Well, an addition is a one pass, you know, series of gates that take the bits and twiddle them and come up with an answer. And then you have multiplication, division, and you have a math coprocessor, and also is able to kind of linearize and compact this multi-bit manipulation into something that if you do factorial, you don't actually have to add n times n times in order to get there. But here, it seems that you do. It seems that those iterations produce more and more quantum operations. And I worry that unoptimized, that means that higher order operations will just be so long that I don't even know if quantum is going to do things any faster, just
Well,
because there's so many quantum operations.
Well, again, your answer is very observant. And, you know, if you go and you look at quantum on the cloud vendors, you know, they're pushing to get higher qubit machines because of that problem. Because so much of this is theoretical, because they don't have enough qubits to be able to realize these potential speed ups, because they run into exactly that problem with the small number of qubits. I mean, even in the IBM environment, there are some of these problems that you can't, from this book, that you can't either simulate, because they say we don't have enough qubits. It'll just error out. Or you try to run it on the IBM quantum environment and it'll say you don't have enough credits. So it's in the development where the hardware is not generally usable yet. You're exactly right, Mary. But kind of like with the speed up of regular processors, there's a lot of focus. There's kind of a, you know, gold rush thing going on. Google just opened their quantum center in Santa Barbara, and Amazon added Bracket, which is D-Wave, because there was money to be made here if they can achieve this. But it's not, as we sit today, it's not in general use at all. So you're right.
I kind of feel like we're in the early Turing machine days, where there's enough math to know what a finite state automaton is, and enough symbolic logic to understand that. And somebody came up with a bright idea of making a proof machine and showing it on paper, but then trying to build it as another 50 years of transitioning from clunky light bulbs to transistor TTL and stuff, and CMOS eventually. Like, I feel we're kind of there on the roadmap. I have no idea, but
We're like close to Thomas Edison. Like, we have a long way to go. We're at the beginning. So
Yeah.
Again, one of the really big areas I know from university students who are studying this stuff is figuring out how to do problem decomposition. So if you go and you like read the papers and stuff, like there was this paper that came out last year that was really interesting from a young woman, I don't remember where, but basically her thesis work was to prove for a certain type of problem that, you know, again, like Nuri was saying, that, you know, it should be theoretically possible when you have a powerful enough machine that it is very, very much faster. And what she actually published is she published work showing how to classically optimize the machine learning algorithm with the hardware that's available now. And she was kind of like the anti-quantum. So it was kind of a notorious paper. Like, yeah, for this class of problems, don't use quantum. So it's interesting because at the elite universities, this is a very big focus because we're trying to get all the young brains on it, basically. But as far as practical, the only place that I hear about it is in, of course, fintech, because fintech has, you know, the money to waste, right? The Wall Streets and all that, where they'll do experiments and try. And of course, they're not publishing if they get anything to succeed, because it's, you know, they're greedy bastards.
IP, yeah.
Yeah. So, you know, we are in the early stages, but again, the reason I'm here is for human health. So I'm kind of, I don't know, cautiously hopeful that, you know, with the sequencing price coming down, and the new types of sequencing, that's going to push the possibilities of quantum. At least one can hope.
the other nice thing is you can have everyone competing with each other to create the best algorithm. And like, you know, oh, I created this awesome new quantum algorithm, and you know, if somebody can come up with a better classical algorithm,
Yep.
and they fight back and forth, and you know, winner takes all. So
This is my fun, to read these papers. I'm such a nerd. It's like, oh, I have to read the paper on that. And I collect them. So, if you guys ever want to get my repository of papers, I have a very big to read on my laptop, and then I have it backed up. So it used to be when I would take long plane flights. So Nuri, I don't know what you're reading when you're flying over to visit, but that's where I would catch up on all that reading. But I'm not doing that lately, so I have to figure out how to catch up on that.
Yeah, that'd be interesting. I was actually playing around with a lot of pandas recently. So I thought, oh, well, on the plane, should I just try to do that or try to do this? Yeah. Yeah, it's I think what you keep bringing up, Lynn, is those genomics. And early in the book, he was talking about how quantum is not it's not an analog computer.
Mm-hmm.
But I think every time you talk about this subject, I'm thinking this is exactly what this was born to do, because the measurements we take in scientific experiments are, first of all, are all statistics because they're noisy,
Mhm.
and we need to do noise reduction, and we need to do line fitting to get the right item. And it's all analog. It's all numbers somewhere on some spectrum. The idea of having to digitize it is half the battle. Then store it is a big expense, and then load it into processing and running combinatorics on it is the biggest thing. So I think that's where the latter part of this, the third one, which is loading boatloads of data and running across many permutations of it. That's
Mhm.
where this is supposed to excel.
Mhm.
So I think that you're on the money. That's where it should be. The quantum is the fit for this kind of problem.
All right. So next thing I wanted to talk about was this intuition thing, which is totally unintuitive. But, so let's see. So we're ignoring the flip part. We're just talking about the mirroring, because the flip can change based on what you're doing. So the mirroring is the important part. And it says, think of the mirror as mirroring about the average of all values. So let's walk through this a little bit. So we have our X and Y coordinates. X looks like is phase, Y is magnitude. So we have for X, for phase, we have 0, 0, 0, and -6, which divided by 4, I'm assuming is -1.53. I didn't check his math, but no, that doesn't make sense. No, it does make sense. Never mind. Okay, so in the magnitudes, we have 0.7, 0, 0, and -0.35, and that gives us an average of 0.088. All right, so on each of these qubits, we have plotted this point. Now, we're going to flip over this point. So where we had on qubit 1 here, or 0, we see that it had phase 0, but now it has phase something else. So we had, I need to see those values again.
Just to correct real quick, phase is not X and magnitude's not Y. He is literally saying X and Y, like on a Cartesian coordinate system.
Oh, yeah, you're right. Yeah,
So that
thank you.
first one that's 0 and then 0.77, it's 0 because on the X and Y horizontal axis, you're dead center.
Yeah, you're right. Thank you. All right, so let's remember these guys. So 0.153 and 0.08. So this is where I don't understand what's happening. So we were at 0, and now we're at 0.306. So it looks like this is the midway point. So this is 0.15. And so continuing down that linear line, we now have 0.306, or right, it's gone twice as much. Now, then we have the 0.08. So I take it we're taking 0.707 minus, or getting the difference between that and 0.08. So that's like 0.699, and then 0.699 minus, I don't know.
It sounds like you're talking about the points in their vector notation and trying to average them in your head. And maybe if you look at it just graphically as what he's doing, there's a point somewhere lying in this circle, and you take the point you were in, draw a straight line to that point of a certain length, right? Whatever distance to that point, and then continue through on a straight line until you hit the perimeter. It's just a graphical straight through intuition. The math was the part that specified which is the mirror point, that 0.306 and 0.053 or 0.53. No,
Yeah.
sorry, that's not the mirror point. The mirror point is whatever it came back in the previous page. But that's all he's doing. He's just saying, look, there's a dot. It's the same location because there's one mirror point for all of those, right? It's the average of all of them. So just draw a line through it until you hit the perimeter. That's where you is.
Okay, that's helpful.
Yeah, I don't know about hitting the perimeter. I was thinking about, like, for that first one, you're taking the empty circle at the top and then drawing it to the black circle, which is the average, and then continuing that exact same distance.
Yeah.
So for that circle, it doesn't change a whole lot, but for the middle two circles that were both 0, now those have magnitude, because you're starting in the middle, going to that black dot, and then continuing through
Yeah,
the
and these
same
totally
distance.
threw me off because I was like, well, how is it determining the phase? But now it's like, now I see it. And it's like, well, this is the starting. We got the starting point is at 0, 0. We have our average.
Point
And-
taken, Jeremy. That's right. The perimeter is the result of going through the exact same distance it took you to get to the black dot, continue on that distance, that draws the perimeter.
Mhm.
Yeah,
Yeah, so we're making a new perimeter basically for all of them.
that's right. That's
Yeah.
and it does have 2 shadings there, the original shading and yeah.
That's why he's saying flip it about that average, which when I first read it, didn't make sense to me, but he's literally saying you're taking your starting point, finding the average. Imagine you stuck a pin right where that average is and tied a string around to your starting point, and you're literally flipping it 180 degrees. So whatever your distance was between your starting and that new average, you're going exactly that same distance literally on the other side. So you're flipping about it. You're flipping about your pivot point there, and that average is your pivot point.
Yeah, thanks for that, Matt. I like the putting the pin in it and string it around. That's very visual.
all right. So is it intuitive now?
I liked his next example because his next example looked more like what we've previously done. Okay, so I have 4 potential outcomes. They all have the exact same magnitude, but I've manipulated the phase of one of them. Why does that suddenly make that one outcome much more prominent? And so when you look at his designs, it's like, oh, now I get it. Because so, yeah, so if you, I felt this example was a little more understandable as to what we've been doing than the prior one.
Okay, so this is the average. We have this black dot as our average. So if we were to flip about that on this first one, shouldn't it be down here? Shouldn't it be at the bottom?
No, you're flipping around about the point, not about the center. So you came from the edge of the pink, and through that black point, you end up at dead center, which is a qubit of 0. It's a magnitude 0.
Yeah, and that big black fat dot at the top really is just to show you kind of where the phase is. That's not
Okay.
actually the magnitude. The magnitude is that the end is that little tiny white dot at the end of the pink part.
Okay, yeah, that was throwing me off. Okay, it's the white part. So if it's here, it's flipping over this, and what, it's ending up at 0?
Yeah, if we think about this as, so if we just had it, then each of these should have like a 25% probability. And so the average of that is, 1 in 4. So if you subtract the average, you end up at 0 for all of those ones that were.
Right.
those
And so
first
this
3.
would be, initially this could have all been 0s, and then there's the hadron that we applied to all of them, which gave them all their averages. And then we were able to flip on that. Those all go back to 0, and this one goes from here, goes all the way up here. That makes sense. That's cool.
And I think, and the main thing here, I think this is, he should have led with this because that's the easy one. The other one was kind of what, it's not on the Cartesian axes, but this one really shows that the phase, the only different one was, bit 4, and the phase flipped into having the magnitude. The magnitude now reveals the one that was quote unquote marked. If we say the phase is the one that's different, right? It's all relative phase, so it's 180 to the rest, and the rest are kind of 0 degrees. So we marked bit 4, and now after doing the thingamabob, it became a magnitude that reveals its markedness.
You're muted, Lynn.
I'm going to point out that we're actually at about an hour. So I'm feeling pretty good about this topic. And, we can continue on, but in terms of the recording, are you guys feeling like this is good for the recording? Dan, do you have anything like key you want to still present, or how are you feeling?
So this is pretty much the end of the chapter.
Okay, great.
So unless there's questions, I don't have anything else.
Great. So the question I have is, who's up next? And thank you, Dan, by the way.
Not
Thank
me.
you.
Not me.
Well, it might be me, so that's why I'm saying it, actually. If no one else wants to jump in, I will take the hard chapter.
Can we design a quantum algorithm for this where the magnitude of whoever's doing it gets bigger the longer it's been since they presented?
There it is. There it is.
So Daniel, circle